This is Professor DuBois from the Professor's DuBois channel, and today I'm going to talk about some more titrations, and specifically I'm going to get into titration of weak acids or bases with a strong acid base. In our previous lecture, we did strong acid, strong base, and I brought this problem up because you should be able to solve this problem just based on that previous lecture. So in this case, we're doing a strong acid, HCl, with a strong base, sodium hydroxide. Now what you want to do is write the net ionic equation. And if you remember, the net ionic equation for a strong acid, any strong acid with any strong base, ends up being H plus OH minus goes to water. So in this question, they're saying that we've got equal molar portions. So if there's equal moles of the H plus and the OH minus, they're going to completely neutralize one another, and we're just going to have product. So the product being water, we would say that the pH would be neutral, or number 2 for this question. Now here's a plot of a weak acid titrated with a small or strong base. And there's a lot of things I want to point out in this slide. So how did I know it was a weak acid? Well, I knew it was an acid because the starting pH was acidic. It's less than 7. So I know that I have, I'm starting with an acid. You'll notice that this curve looks a little bit different in here than the strong. We have this long region. So down here it says volume of NaOH added, so that's the strong base. So I'm going to write a net ionic equation. That's down below. So I've got my acetic acid. I got that from up here. It's a weak acid. Plus the strong base. Now we don't break apart those weak acids, so this is the entire acetic acid, not H plus like a strong acid. So the strong base, OH minus, and what happens is we end up with conjugate base. Now remember, with the strong, our product was just water. Well, now we're producing a conjugate base. So, well, what does that mean? Well, if we're adding a small amount of the hydroxide ion and it gets consumed, we're producing this conjugate base, and what we're creating is a buffer solution. We've got a weak acid and its conjugate base, and you can see that buffer region in this area here. This is what we call the buffer region. Another thing that's worth pointing out is the equivalence point has a pH that's, it's greater than 8. And remember, with the strong, at the equivalence point, we had a pH of 7. So why is that? Well, at the equivalence point, equal amounts of acetic, equal amounts of the hydroxide ion, they completely consume one another. Well, we've produced this conjugate base. So if I take that conjugate base in water and write this reaction out, you'll see that we produce hydroxide ion, which is basic. So at the equivalence point, in the presence, we'll have the presence of this conjugate base, which is slightly basic, which moves that equivalence point pH up greater than 7. So that's a useful tip. Now, there's something that we like to talk about. It's called the half equivalence point. So I can find that spot by looking at the volume at the equivalence point, which is 100 mils. And if I take half of that volume, it's 50 mils. And so I'm on the line right in this area. The half equivalence point, and you'll have to imagine maybe we had 10, we'll just say 10 units of acetic acid, and we added 5 units of hydroxide, right? So that's half of the equivalence point would be 10 units of hydroxide. So if I added 5 units, they'd be completely consumed, leaving me with 5 units of acetic acid, and I'd produce 5 units of conjugate base. And if I put this into my Hasselbalch equation, I would have the pH equals the pKa plus the log of 5 over 5. Well, that's the log of 1, which is 0, so the pH equals the pKa. So this can be kind of useful. If we can find the half equivalence point, we can get the pH, we can read it off the scale, which is the pKa, and we could use that value to determine the Ka for that acid. So here's just kind of some words, some of the stuff I talked about, and I'm going to move on. Now I've got a weak base titrated with a strong acid. Well, how do I know it's a base? Well, look where I started. I've got a pH way up here at 11, and so I know it's base. Now, if it was a strong base in a strong acid, I know that the equivalence point would be a pH 7, and you can see here that the equivalence point pH is 5.28. So again, I took the I can get the halfway point here, and that's the half equivalence point, and that's where the amounts of my base, they're saying that the weak base was NH3, the amounts of the base in the conjugate would be the same. So the pH, well, in this case, would be equal to the pKa of the NH4 plus. So we can get that information from these plots. So again, here's the word slide that I'm not going to spend much time on. This is a pretty good summary slide. So if we look at a titration plot, look at the starting pH. That tells us if we're titrating, if we're starting with an acid or a base. Then we go to the equivalence point. So if the pH is equal to 7 at the equivalence point, strong, strong. If the pH is greater than 7, it means we have a weak acid, strong base. If the pH is less than 7, it means we have a weak base with a strong acid. We're not going to do weak, weak. That'll never be an option. So we're going to have one strong in all of these scenarios. So we can, also worth noting, we can calculate KAs from pKas, and we can get KBs from KAs using the relationship shown at the bottom. This has to be a conjugate pair, so we can't just take any acid base and get a K value. We have to have conjugate pairs to use that relationship. This is a polyprotic acid, meaning it has more than one donatable hydrogen. It's kind of small, but we're starting with H2C2O4. So we have this first equivalence point. It's a little bit tough to, it's not quite as nice as the second one, but you can see there's something funny going on here. So when you see this type of plot, you can predict, if we have a polyprotic acid, in this case, started with low pH, right? So and that equivalence point was really low, wasn't 7. And so the first hydrogen leaves us with the conjugate base, HC2O4 minus. Well, when this is all gone, then this second hydrogen can come off and we'll have C2O4 2 minus. So here's a problem where it says what is being titrated in the diagram below. So first thing we do is look to the axis. What's the starting pH? Starting pH is very high, so we have a base. Now, we don't know if it's a strong base or a weak base, so we'll go to the equivalence point, and I wrote that in for you because it's so small. The equivalence point is pH is 6. So what we have here is a weak base reacting with a strong acid, or choice D. So when we do these calculations, there's a whole series, and this is a word slide, there's a whole series of questions that can arise from these. Now, you might not have to do all of these questions. Maybe this could be written as just one question, but I'm gonna go through a slide that has a whole bunch of scenarios, and I'll do some of the other ones, but this is kind of a guide that you can use, and let's just get started. So this is the question. I've got lactic acid, and they gave me a pKa, so that's a weak acid, not one of the strongs. And I'm going to titrate with a strong base, potassium hydroxide. So I've got all these different volumes. Now this question, this is written like a titration, right? Like we're adding these different volumes in and then calculating the pH. Now this could just be, it wouldn't have to be a titration. They could just say, what's the pH if I mix 25 mils of 0.1 molar lactic acid with 20 mils of 0.1 molar potassium hydroxide. So we've kind of covered this already, strongs and weaks, but for this one, we've got a whole slew of different questions, and you should be able to work through these. I did a few of them. I left a few for you. I have all the answers, so I'll just kind of talk through these fast. So initially, they want to know what is the pH after no hydroxide's been added. So all we have is this weak acid, lactic acid, and I was a little too lazy to look up the formula, so I just called it HA. You know, there's my proton acid. So I wrote a net ionic equation here, and the molarity is 0.100 molar. So I'm going to use an ice table and just have the one thing, and I can solve for X. We use the assumption rule and say that at equilibrium, the amount of that lactic acid is about the same, and I can solve for X, and then that will be equal to my hydronium ion concentration, so I can take the negative log of that to get the pH. pH is 2.43, and that makes sense because it is just a weak acid. So when I start adding base, I'm going to expect to see that pH go up. Okay, now I'm going to do C. I circled it on the left, 12.5. I need a mole table, and I also need to write the reaction. So what's going on here? So I've got my reaction here, HA, and this is a net ionic equation with the OH minus from that strong base, making the conjugate base of my weak acid plus water. I need to go to moles because I'm adding volumes. I'm changing this volume, mixing things together. So when I calculate the moles, I showed that up here for the lactic, for the OH. I put them into the table, and this is a single arrow, goes in one direction. This is not an equilibrium. There's no X. So we're going to subtract by the smallest one over here. So this reaction is going to run until something runs out. In this case, it's the OH. There's less of it. So we're going to subtract the 0.00125 from both. We're going to add it to the other side. And now we have equal values. So this is the half equivalence point. We're halfway to the equivalence point, and so the log of 0.00125 over 0.00125 is equal to 0. pH is equal to the pKa, and they gave us the pKa at 3.86. Moving on. This one's E, 25 mils being added, so same approach. I'm going to calculate the molarities. Take a look at this. This is the equivalence point, equivalent amounts. This is the hard one. So all I have left is my conjugate and water. So I take this amount of conjugate, right, and this is moles. I'm going to convert that into molarity using the total volume, 25 mils and 25 mils, 50 mils, and I've got my molarity now. And now I can put this molarity into here and do an ice table. I've got 0, 0, minus X, plus X. This is about 0.05. Solve for X, and I can get the X is the OH minus concentration. So I can get the POH and then get the pH at 8.2A. Running out of time, so I'm going to move quick. I'm going to do the last one here, adding 30 mils. So what happens, I convert these to moles. The HA is the same. It's been the same for all these questions. So my hydroxide ion, I showed that here. I took the 30 mils, converted to liters, used the molarity. I've got the moles. I put this in. Now take a look at this. Now I've got excess hydroxide, excess strong base. So even though I've got some conjugate base over here, this will not contribute to the pH. So if you have excess strong, you're going to go right to the strong and calculate your pH. How do I do that? I'm going to take this number of moles that remains, divide by my total volume. So I had 25 from the weak acid, 30 from the base, and I convert that to liters, get my molarity, negative log, gives me the POH, subtract from 14, and I've got my pH. So I'd strongly recommend giving these a try. I'm going to put the answers up on the next slide, and I left a couple of them. I didn't work out, so work through these. Very good practice, strongs and weaks. So here are your answers, and thanks so much for tuning in to the Professor's DuBois. Stay tuned for more mini lectures.